Design the triggering circuit of figure. The parameters of UJTs are Vs is 30 volt, N is 0.51, IP is 10 microamps, Vv is 3.5 volts, IV is 10 milliamps. The frequency of oscillation is a fixed hertz and the width of the trigger impulse Tg is 50 microseconds. Assume Vd is equal to 0.5. So we need to calculate the values of R and C, RB2 and RB1 for these specifications. The frequency of oscillation is 60 Hz, meaning we need to generate firing pulses after 1 by 60 seconds. The firing pulse period frequency 60 Hz means after each 1 by 60 seconds we need to generate firing pulse. So 1 by f 1 by 60 Hz, so 16.67 millisecond is t. Okay, what is the formula for t? T is 1 by T is RC ln 1 by 1 minus eta. So T already is known to us, C we need to assume it, R we can calculate, eta is known to us. But before we do this, we need to find out some limits of R. So we learned already R should be less than Vs minus Vp divided by Ip. So, and R should be greater than Vs minus Vv divided by Iv. First, R should be less than Vs. Vs is given, Vp is not given, but we can calculate Vp. Formula is eta into Vs plus Vd. Eta is given, Vs is given, Vd is given, so Vp we have calculated. So by substituting that Vp here, Vs is 30, Ip is already given, Ip is 10 microamps, 10 microamps. So R should be less than 1.42 micro. Then R should be greater than Vs minus Vv divided by Iv. So R should be greater than 30 minus Vv. Vv is somewhere here 3.5 volts, 3.5 Iv. IV is 10 milliamps, 10 milliamps, 10 milliamps. You substitute 2.65 kilo ohm we got. Okay. So these are the limits. R should be less than 1.42 megohms or should be greater than 2.6 kilo ohm. So T is equal to RC ln 1 by 1 minus eta. So T is equal to RC, you assume it 0.5 microseconds ln 1 by 1 minus eta. So we can calculate R value 46.7 kilo ohm. So what is a TG? So TG is because width, the RB1 affects on your width of the triggering pulse. This is the width of the triggering pulse. See here, this is the width of a triggering pulse. The trigger discharging path C and RB1 comes into picture in discharging path. So triggering pulse Tg width is equal to RB1 C. C we have already assumed 0.5 microfarad, so we can calculate RB1 100 ohm. RB2, it is an empirical formula, 10 to the power 4 into N eta into Vs. Eta is 0.51, Vs is 30, we can calculate RB2. So all the values we have calculated. Then next topic is dV by dt protection. See, we need to protect our SCR from dV by high dV by dt. If there is a high dV by dt, what do you mean by dV by dt? In the last class we have studied what is a dV by dt. We are modeling SCR like this, correct? 2 transistors and 3 junctions of a SCR we are modeling as 3 capacitors. But when SCR is forward biased, in the sense when anode is more positive than cathode, junction J1 is forward biased, junction J3 is forward biased, junction J2 is reverse biased. Okay, so now, so all 3 junctions J1, J2, J3 are acting like a capacitor, CJ1, CJ2 and CJ3. So it's here CJ2 effect is dominant. So we have studied that if there is a if you are applying rapidly raising voltage to anode and cathode of SCR, means if you are applying here, it is applied to anode and cathode of SCR. So what happens? Middle junction J2 is reverse biased, most probably. So charging current flows in that junction, in that capacitor CJ2. this charging current flowing to that capacitor will increase ICBO1 and ICBO2. ICBO1, ICBO2 will increase the values of alpha 1 and alpha 2. Again alpha 1 and alpha 2 increases, again IA will increases. IA increases means again alpha 1 and alpha 2 will increases. So this is a positive feedback effect. So large IA will flow, or else I can say that SCR will turn on. Remember, even though we have not applied a gate pulse, SCR will turn on only because of high dV by dt of applied voltage. Means if you are applying rapidly rising voltage to anode and cathode of SCR may turn on. This is unwanted, so we need to avoid it. So last class we have learned it. Charge in the capacitor of junction J2 is Q. If you have charge flowing per unit time is itself is a current. So in formula this you can write using like this. So here we can see d by dt of Vj2 means the current which is flowing in junction J2 is entirely depending on what is the rate of change of voltage with respect to time. Okay. So we need to protect our SCR using capacitor. Means simple here, we rapidly rising voltage we are changing to slowly rising voltage. You can see here, assume that if you are applying a voltage like this, assume that it is a voltage. If you take a slope of this waveforms, it is very high because rapidly it is rising, and this form of voltage we need to convert into this form, slowly varying voltage. How we can convert means using a capacitor or connecting a capacitor parallel to that SCR. So if assume that there is a voltage sources here, what happens if current is flowing here? So if assume that this switch is already closed, so current will, SCR is already off, current will flow through this capacitor and load. Capacitor and load. Then so this is a current which is flowing in this way. We need to find out what is an equation of this current. So you just apply Kirchhoff's voltage law here. Listen here. Here we are having PS, and we need to find out what is the current which is flowing here. We should assume that this switch is closed. Whatever current, okay, you apply Kirchhoff's law, value of this you assume as Vs. So Vs minus 1 by Cs into I dt minus R into It. That is, the capacitor voltage is this is leaving, and here is plus, correct? Kirchhoff's voltage law, plus, here plus, minus, so that's the reason here again plus, minus, so Vs minus 1 by Cs I dt, that is a voltage across capacitor, and R into I of t. So this is an equation in time domain. So then you just write like this. So now to this time domain equation I am applying Laplace transform. Then I will write the equation in S domain. Laplace transform of 1 is 1 by S, correct? We learned it, Vs by S. Laplace transform of I of t is I of S. Integration is there. Laplace transform of integration of f of t is f of s by s. If you are assuming that initial voltage stored in a capacitor is 0. Initial charge stored in a capacitor is 0. So due to assuming that, I will write I of t as changed to I of s. Because of integration, there is a s in denominator, 1 by cs minus r into I of s, 0. Okay, so vs by s minus is 1 by cs plus r is equal to 0. Okay, so vs by s is 1 by cs plus r, vs by s, so you just rearrange it, is you keep outside, 1 by cs plus r, vs by s I of s 1 by cs plus r, vs by s is 1 plus r cs s cs s. Vs is 1 rc 1 by rcs plus s divided by cs. Here we can see that s and s is cancelling each other, so vs is rcs 1 by rcs plus s, because here you keep s alone here, and you for that reason you keep outside rcs outside. So this again vs is r 1 by rcs plus s. Okay, so I can rearrange this as I of s vs r 1 by rcs plus s, I of s vs r 1 by rcs plus s, I of s vs r 1 by rcs is tau, rcs is tau, I am assuming rcs as tau, so plus s, I of s is vs r, so you assume that 1 by tau is alpha, so alpha s, so what I am assuming here is rcs I will assume as one symbol tau, and 1 by tau I will assume as alpha, so vs by r into alpha plus s, so is vs by r into s plus alpha. So this is in a standard format. Now you can apply a inverse Laplace transform easily. You I of t, this s domain you once again you convert into a time domain, I of t vs by r e power minus alpha t. Now okay, so now we got the equation for a current which is flowing in this loop. This current equation we got, correct, this current equation we got, so assuming that this is closed, so if this is vs, the current which is flowing here, is okay, what is the voltage across this capacitor? Voltage across this capacitor is vs minus the voltage across this resistance. Okay, so voltage across this capacitor is vs minus voltage across this. What is the voltage across this resistance? The current which is flowing here, that is, which is that current? That is an I of t, correct, y of t, I of t into resistor. Okay, I of t into resistor, so vs minus I of t into resistor, vs by r, you already calculated this, f into r, so vc is, we got a formula vs r cancel, e power alpha t. So now the what is the voltage across this capacitor? So we can see that if you plot this, we will get this waveforms. This is a voltage across capacitor. Same voltage we are applying to anode and cathode. That's the reasons we are saying that anode to cathode voltage is same as this. So now dv is voltage across capacitor is vs minus vs by into e power minus alpha t minus alpha t. Okay, so now dv is voltage change in voltage, means we should calculate the difference between this dv, means this voltage, this value we need to calculate, this is dv. What is this? This is voltage at capacitor when t is equal to tau, means voltage at capacitor when t is equal to 0. Voltage at capacitor when t is equal to 0. So Vc is Vs minus Vs e power minus alpha t. So you just say that when t is equal to tau is equal to RCS, what happens? This is a value when t is equal to tau. This is t axis, this is independent axis t. What is we are doing here? When t takes the values of tau, what is capacitor voltage? This capacitor voltage is this. So we are calculating that. So when V of C, so what is dV? The voltage of the capacitor when t is equal to tau minus voltage of capacitor when t is equal to 0. So what is the voltage at capacitor when t is equal to tau? So we should substitute this. So this is Vs minus Vs e power minus alpha into tau. What is voltage of capacitor when t is equal to 0? So Vs minus Vs into 0. This. Anyhow, e power 0 is 1. So Vs. So this will get cancel each other. So what is remaining here? Vs minus Vs into e power minus alpha tau. So Vs minus Vs into e power minus alpha tau. So this is remaining. So you just substitute, this is dV. So what is an alpha value? What is an alpha value? Alpha is 1 by tau. So dV is Vs 1 by tau. So this tau cancel each other. So Vs e power minus 1. What is e power minus 1? 0.3678. Vs minus 1. So what is dV then? dV is 0.632 Ps. So what is dV? This is dV. This dV is how much? 0.632 of Ps. What is dt? dt is tau minus 0. Tau minus 0 is tau. What is tau? We have considered tau is what is R and Cs we have considered as tau. So if you are what is dV by dt? 0.632 Vs R. Yes. So this is a mathematical equation describing the dV by dt of this when you are applying a capacitor of this and R of this. Okay. So when so we have learned what is dV by dt. Okay, this is a simple term. Next, so we have solved. We have learned here. We have reduced the dV by dt by connecting a capacitor across SCR. Okay, but this will cause some problems. Assume that whenever SCR is in off, yeah, this capacitor C we have used to reduce the rate of change of voltage, correct? So rate of change of voltage, but after some times this is used in any of the circuit, no? We are applying a gate pulses and we will turn on SCR. What happens? Already charged capacitor will discharge like this. Assume that there is no resistor here, like in this circuit. What happens? The charged capacitor will discharge. So it is charged to source voltage itself. So in the discharging, capacitor is there and it is discharging. It is just like, see, there is no resistance, so very high current flows. This may damage your SCR while discharging. So we should avoid it. Means we should discharge current, we should reduce it. How? We are connecting one series resistor here like this. Now what happens while discharging? So in discharging path, if it is charged to Vs, what is the discharge? Vs by Rs is a current which is flowing. So Vs by Rs is a current which is flowing here, which is flowing in this, so that we can save the SCR from discharge current, Okay, so this is one alteration we are doing to this circuit. So whatever this circuit we call as a snubber circuit, so connecting capacitor across SCR, again along with this R. Okay, so but okay, I told already why R we are using. Okay, so this is just to save SCR from discharging current, so to reduce the discharging current. Then since sometimes load is R as I shown previous, sometimes load may RL, then in that cases circuit looks like this. So here if your load is a motor, the winding, that motor winding is acting like R and in series L. Okay, then sometimes stray inductance also we should consider. If you are considering the stray inductance of a circuit, my entire circuit looks like this for an RL load. So next, so here there is a one trick here. As I told earlier, if you connect when you are connecting a resistor in series with capacitor, as I told, it is parallel to SCR. So we are connecting this you just right now, just as I told earlier, like this. Now what happens here, if you are using a big R here, a little high R, what happens? Charging happens very slowly. Charging should not be very slow. If it is charging is very slow like this, what happens? My circuit operation will disturb. Circuit operation will be disturbed. So to avoid that, so charging should be slow, but it should not be too slow. But discharging current, if it is very small, then it is good because it will save my SCR. So here we are using 2 resistor. So you can see when I close the switch, charging takes place in this order because here there is a power source. So this is diode is forward biased, charging place. While charging, only R1 plays a role. So we will choose adequate R, so that how much what should be the dV by dt. It is not so very small also, it should not be very high also. Okay, then so discharging time means when SCR is on, discharging should happen, no? Capacitor voltage should discharge. So for that we are using this another resistance here, see R2. But this R2 not comes into picture whenever during charging process, because diode is there here. Diode will short circuit this, so charging happens only this. But discharging not take goes in this way. Discharging takes in this way because there is a diode there. So while discharging, these 2 resistance play a role, while charging this resistance only play a role. So we can control the discharging current, and as well as we can control how fast charging should happen. Okay, this is one tricky circuit. Thank you.